So today I'll go through chapter 2, which is just one parameter models, and next week we have then multi-parameter models. But with this one parameter models, going through then some of these important concepts, and in the lecture there's more about priors than in the book. So last time I used the example of drawing a coin or having chips in the back, and then one event could be then that I pick one chip, and then probability of getting red chip would be theta. Then next time I pick yellow one, and then the probability of that one is 1 minus theta. So we have these two possible choices now in this case. Either it's red or yellow, and probability theta or 1 minus theta. If we now keep picking up these chips, we know that the probability of getting a red is theta. Probability of getting two reds in a row is theta times theta. Then getting yellow multiplied by minus 1 minus theta, and so on. We get this sequence of probabilities, independent trials. We can just multiply these probabilities. But multiplying these probabilities, this is now for a specific sequence. But we are often interested in not in specific sequence, but just how many red ones we observed, how many yellow ones. In medical testing some treatment, how many died, how many did not die. It doesn't matter for that one in which order people survived or died. And if we don't care about the order, then all the possible orders are fine, and then we multiply then with this combinatorial n over y term. And this then gives us the probability of observing certain number of reds or certain number of deaths if we know the probability of theta for reds or deaths. And so we have the theta exponented to y, so it's combining all the theta terms in the product, and then 1 minus theta exponented to n minus y. And n is the total number of observations. And this is now the observation model. And now this is discrete for y. So if we have fixed, let's say that I pick 10 times a chip, then for different number of reds I could pick with the 10 repetitions. This is discrete function. If I do just one pick, possible choices for y is either I get 0 reds or 1 red. And if I would tell that there's an equal number of red and yellow chips, then we would have the same probability for both of these observations. If we have still the same, that there would be equal probability for red and yellow, and then make 10 repetitions, this is discrete distribution and showing how probable it is that certain number of reds would come up with 10 observations. And on the other hand, if the theta, so there's 90% of chips are red, then this discrete distribution has higher probability for the large values. But these are now for the observation model. Then we want to know something about theta. In back of chips example, we have a finite number of chips, so theta is not exactly continuous. We could switch to idealized roulette. So there's a circle, and then we have arrow, and then we could divide this to some parts. We could divide it in 50-50 and then roll the arrow, and what the probability it would be that it lands somewhere. And then we would think that this is continuous now, the theta, and we can continuously divide this to different kind of the slices. Or if we think about the probability of death, it's likely that there we can also think about theta continuous. So from the Bayes rule, also shown last time, on the top of the line we have this py term, which was the observation model. But if we put that function which described the observation model there and fix the y and then look at this as a theta, then that term is the likelihood term. We need the prior, we need the normalization term, and then we get the posterior. So what we know after getting observations about theta. Normalization term is just integral of the what we have top of the line. So integrating over what we have top on the line, we guarantee that then that integral over the posterior is 1, which is then the kind of the denotes the all the probability mass. We can simply, for simplicity, start with the uniform prior, assuming different theta values are all equally likely between 0 and 1. And then on top we have only then this function which was describing the observation model, and below hand we have some integral. Now it is common that this below hand integral is just denoted by capital Z in a way that it's not necessarily needed right away. But in also now we can put also this n over y, that combinatorial term. It's also something that doesn't depend on theta. We can put that also in this capital Z. So then as a function of theta, we have there's 1 per z, and then only those terms which depend on a theta. And y and n are observed based on how many draws we had and how many reds or deads we observed. The normalization term can be also derived. It has analytic form. In general, getting these normalization terms, it's not trivial. There's not always analytical form, and that's why we also in this course eventually go to using Markov chain Monte Carlo methods. But now it happens that when we integrate from 0 to 1 this function, then we can present it with gamma functions, and with integers these gamma functions are same as factorials. Even then, when we use computers have a limited kind of range what kind of numbers can be accurately presented, and then usually log gamma terms are computed when we have large integers. And then, since each of these gamma terms there are big, but then we are dividing big gamma terms with another big gamma term, then actually usually this ratio is not that big. And so we get this analytic form of the posterior, and then for example, if we have observed 6 red ones with 10 picks, we get this kind of posterior distribution, which is called beta distribution. And you can see the beta getting 2 arguments, y plus 1 and n minus y plus 1. Why there's the plus 1? It's convenience, but also we'll come back later how it relates to this prior information. And now you can imagine then that with different number of observations we get this posterior distribution in different places. With just 10 draws, you can see there's a lot of uncertainty. It's almost somewhere from 0.2 to 0.95 range. So we have not learned much from just 10 draws. This is characteristic for these binary observations, binomial models. They are the functions you find from R for computing densities, cumulative density functions, quantiles, generating random numbers for these from these distributions. Also, sometimes I come back to these computational issues since I have a computer science background. This beta CDF is not trivial to compute, for example, in R. So cumulative density function was that when we have the beta distribution, it was easy to compute if we want to compute the integral over from 0 to 1. But it's not easy to compute if we want to compute the integral from 0 to some other point. And then, for example, in R, p beta function uses continuate fraction with weighting factors and asymptotic expansion. And these are, of course, also kind of what is used depends also, again, accuracy of floating point numbers. In a way, how to compute this is the simplest possible model. And already for the simplest possible model, there's no analytic solution for computing cumulative density functions, which is useful when making inference. And then it's not easy to come up with these continued fractions. And like Laplace developed this normal approximation, which is also then sometimes known as Laplace approximation, because he didn't know how to compute beta CDF. The book has then the example of Laplace analyzing the ratio of girl and boy birds in Paris, and making this finding out the beta posterior, and then wanting to find out what is the probability that theta would be larger than half. And then for that probability that it's larger than half, needed to compute the cumulative density function, but then use the normal approximation. For you, it's easier than with the computers. And also in your assignment, then you have this week this binomial example. This example is also in book. Just now, a little bit more than 400 and 500 girls and boys, and we get the ratio 0.445. And then we know that in modern Western countries, the population average in different countries is quite stable, and the reference value is then 0.485. And now we would like to know then, does the placenta previa affect this ratio? So placenta previa is where the fetus attaches to the place in uterus. And we can then, the posterior beta is so 437 plus 1 and 543 plus 1, and we can plot it. There's a 95% posterior interval, there's the reference value plotted, and then we can compute the probability that theta would be less than this population average. So there's still some probability that also above that reference value. So this is not completely conclusive, but it seems that it might be. It's quite likely that there are now more boys than in the usual population. So far we used uniform prior, and I also last time mentioned that often as a benefit of Bayesian approach is mentioned possibility to use priors, and yes, that's one, but also very important part is the integration over the uncertainties. If we want to now predict distribution for new y tilde, so now this could be just, for example, that kind of the distribution for how many reds we observe when we pick the next one, or in this case, what is the probability then that y tilde is one red with one extra pick. Given that, so if we know theta, then that's easy. It's just theta. But since we don't know theta, we can weight each of these probabilities that it's red one by the posterior probability of theta. And then we integrate over the range of theta. And we get posterior predictive distribution, which is not conditioned on theta anymore, but just on the what we observed. M there is referring to model, reminding that these all the time when we are making these inference, it depends also on the model assumptions prior and also. So the probability that the next one is red, given theta, is just a theta. And then integral over theta given this density. So we have the probability density and then theta, and we multiply then and integrate, which is then actually gives us what's the weighted average of theta. So just the expectation of theta. With uniform prior, this would be 1 plus y plus 1 divided by n plus 2, which is interesting in that sense that now this integration is already regularizing our inference. Extreme cases. What if we have so far observed 0 red ones? What is the probability that the next one is red? It's 1 per n plus 2, so it's not 0. Or if we have observed so far all reds, what is the probability that the next one is red? It's not 1, it's something just below 1. So this integration is regularizing. And here with this that what if we've so far observed all red ones, you can see the mean plotted there. Integrating over this uncertainty is regularizing our prediction. We'll come back later in when we discuss chapter 9 about the costs and utilities, decision making. We'll come to kind of the alternatives in a way also, how we can combine integration over the uncertainties and then utilities and cost of different choices. And here you can see that now the kind of the maximum a posterior choice, which now in this case the posterior is actually the same as likelihood because we had uniform prior, that maximum choice would be, say that the next one is with probability 1 red. So I just previously I discussed posterior predictive distribution, but there's also useful prior predictive distribution. We can also look at what would we predict just based on our prior information before we have observed any data. This is useful when building models. This is useful when we are doing design of experiments before we have any observations. And then the posterior predictive distribution is specifically useful then making predictions after we've learned something from data. We can also, thinking about this prior predictive distribution, it can also justify the uniform prior for theta in this binomial model. So if we want that the prior predictive distribution to be uniform, have the same probability for each outcome. So for example, with the pack of chips, if you don't know what is the ratio of red and yellow ones, and you would say that, okay, if I pick 10 out of there, it's as likely to observe anything from 0 to 10 red ones. And then you could compute from that, okay, your prior has to be uniform on theta then. And we can use also, with more complex models, this justification that what we know about observations, in which range our predictions should be, and then go back and what kind of priors we would like to have for model parameters. Alternatively, think that just all the values of theta are equally likely. So that's also option. So in the book, there are different priors mentioned in slightly different places, and these are all kind of useful terms. And I made this slide just that it's easier for you to find a specific page which discusses specific prior. After we finished this third edition, we've learned more about priors and especially about weakly informative priors. And then there's additional information available in our prior choice wiki. Conjugate prior, the name comes that prior and posterior have the same form. So I already told that the posterior for binomial model is beta. So then you can guess that now the conjugate prior in that case is beta prior. There are conjugate priors only for exponential family distributions and only then some irregular cases. This used to be very important for computational reasons, and that's why it's also in like chapter 2 and 3 and 5 it's still shows this importance. Also, first probabilistic programming framework PAX, which started the beginning of 1990s, the computation there was based much on these conjugate priors, and then later we come to this keep sampling, which can be made efficient with these conjugate priors. But then with these modern probabilistic programming frameworks using like dynamic Hamiltonian Monte Carlo, example STAN, there's no computational benefit anymore. People are still copying old models, old priors, so you can still see a lot of conjugate priors. But it should be in a way that when you are learning Bayesian modeling, you can just focus on what would be that distribution which describes in the best way our prior information. There are still some computational reasons to favor certain priors in a way that if you are not kind of the it's like quite common that in priors we don't have enough information about tails, and then if you are not certain what kind of tails to choose, then it's likely that it's useful to choose that kind of priors with tails leading to some computational advantages. It's likely that it doesn't affect your inference much because kind of that's the part where you didn't have information overall. We'll come back to these details. So for binomial model, posterior is beta, so prior has to be beta also. I've used here the proportional 2 so that we need to have only those terms which depend on theta. And you can see the posterior is now then the likelihood times prior, and then we can combine. And now you can see we still have the y and n minus y terms there, and then we have alpha minus 1 and beta minus 1 there. And then when we write it in this beta form and the specific arguments for the beta prior, we get alpha plus y and beta plus n minus y. When we had the uniform prior, we had y plus 1, so alpha was 1, and we had n minus y plus 1, so beta was 1. And if you put alpha equals 1 and beta equals 1 to that beta distribution, you can see there's theta exponented to 0 and 1 minus theta exponented to 0, which is uniform. And we can now consider this alpha minus 1 as a number of prior observations. So this is also kind of part of the chain rule thing that in Bayesian inference, when we get posterior, that posterior can be used as a prior for the next thing. So if we observed something, or if we have some knowledge which can be presented with the beta prior, we can think them as prior observations, and we can that way kind of evaluate how strong prior is compared to the information from the data. Here are plots from the placenta previa example, and you can see that you can remember that there was about 400 and about 500 girl and boy babies there, and then if we now add a prior centered on known general population average, so 0.485, you can see that how this prior gets narrower when kind of the alpha plus beta gets higher, larger, and how then the posterior starts to get towards our prior. But you can see also that even with the kind of the prior to the last one, saying that, okay, before seeing any data, we would say that there's not so much changes in different conditions. And this is kind of what's been observed. With the humans, it's very stable, and this is already quite weakly informative prior if we say that in some specific case, the ratio of girl and boy babies would be something from 0.4 to something almost 0.6. That's already quite weak. And then that is not changing much our inference. It's slightly changing the mean of the posterior, but you can see that, for example, the cumulative density is not changing much at there. So we would need to make this prior quite strong before our conclusions about this placenta previa would change. So yes, it is useful also to have these priors. When we have more complex models, the priors become more and more important. Also, with simple models, there are certain cases where priors are very important. Here you can see that if we add even weak prior in binomial case, we exclude now the extreme case that theta could be 1. So adding even that weak prior is regularizing it away from 1, and of course it would regularize it away from 0, 2. But you can see also that when we integrate, the mean changes less than the mode. So it's also that after the integration, our inference is also more stable. This is also kind of the overall why Bayesian modeling works often better is that it's more stable given small perturbations in data because of this integration. Specific example where this kind of prior information would be important and just the integration is not that helpful would be rare diseases. There's some rare disease and we go to a new country. We observe 1,000 persons in a new country and none of them has this rare disease. Yes, we could just use uniform prior and then integrate and get some prediction how likely the next one is. But of course it would be much more useful if we know from other countries how rare that disease is to estimate for the new countries also. And then in chapter 5 we go to hierarchical models, which makes it even quite easy then to have these kind of models where we share prior information between different countries. These are kind of bit boring things now that we can compute these easily with computers, but there happens to be analytic posterior mean for when we are using this conjugate prior. Maybe interesting thing is now that we can see that it doesn't matter what our prior information is. If the number of observations grows to infinity, then again our inference is just based on observations. Posterior variance, again there's analytic form, and the interesting part here is then that posterior variance goes to 0 when number of observations goes to infinity. So priors are useful, but if we happen to have infinite amount of data, the data always then decides. Okay. Let's have now 10-minute break and continue more with priors and then a little bit about one-dimensional Gaussian.